Let us continue with the fundamental concepts in organic chemistry, the basic principles that are used in organic chemistry. In the last lecture, we were looking at the electronic effects in organic chemistry. In the electronic effects, there are 4 types of effects. We already considered the inductive effect and the electromeric effect. With suitable examples, we have seen this. This is a permanent effect. This is a temporary effect. This is observed only during the course of the attacking reagent approaching the substrate molecule undergoing a particular reaction, for example. The third effect is what is known as a resonance effect. Or effect. The resonance effect is a very important effect in organic chemistry, and this is also a permanent effect depending upon what kind of groups are attached. You can classify the groups into electron donating groups, which will have plus or effect, in other words a positive resonance effect. You can have electron withdrawing groups, which will have minus or effect or a negative resonance effect. Now, what is resonance? Resonance is essentially delocalization of electrons particularly of the pi electrons without changing relative positions of the atoms. In other words, you are not allowed to move the atoms around, the atoms stay in the same place, whereas the electrons can move from one position to another position. In other words, you can delocalize the electron density around the molecule. So, this is a very important concept, namely delocalization of electron. Let us illustrate it with a simple example of a carbonyl functional group. Now, what would be a resonance structure of the carbonyl functional group? Remember, there are 2 lone pairs of electrons on the carbon. The pi bond in the carbonyl functional group is more mobile than the sigma bond. So, it is possible to delocalize the pi electron. If you were to delocalize the pi electron in this particular fashion, this would correspond to the resonance structure of the carbonyl functional group. One can also try to delocalize the electron from here to here where the charge reversal takes place, for example. Now, this is a neutral structure, and these are the delocalized charged structures of, let us say, a carbonyl functional group. Now, important rule in doing the delocalization business in the resonance structures is that you cannot violate the octet rule. Now, if you look at these 2 structures, the Lewis structures that are drawn here, if you look at carefully, because of the electronegativity difference between oxygen and carbon, you have a valid reason to delocalize the electron onto the oxygen, because oxygen is more electronegative. In doing so, you are also not violating any kind of an octet rule. This is octet, all right. This is sextet, but with a carbonium ion, so it is all right. So, one cannot violate the octet rule, but if you look at this particular structure, the carbon has 10 electron around it if you look at the Lewis structure of the carbon itself, and it bears a negative charge also. So, this is not a valid structure at all for the resonance structure, and this is the only valid structure, resonance structure, for the carbonyl functional group. So, I hope this is illustrating the essence of the, we are not changing the positions of atom in any of these things. The relative positions of atoms are essentially same. We are only delocalizing the pi electron to develop charges, and as a result of that you have a concept of resonance coming into picture. Certain compounds, a fixed Lewis structure alone cannot explain the property of the compound. I will illustrate this with this example. When a carboxylic acid ionizes to give a carboxylate, the carboxylate ion is written like this. Normally this is how you write the carboxylate ion, and this would be the Lewis structure of the carboxylate ion. There are 3 lone pairs of electron on the oxygen bearing the negative charge, and 2 lone pairs of electron on the oxygen bearing the no charge. Now, if you look at the carboxylate ion, this is a single bond and this is a double bond. So, the bond length here should be different from the bond length here. However, spectroscopic evidences show that the 2 bonds are of the same length, both spectroscopic evidences as well as X-ray crystallographic evidences, where you can actually measure the bond lengths. There is no difference between this carbon oxygen bond and this carbon oxygen bond. So, this structure alone cannot explain why the bond distances of the bond lengths of the carbon oxygen bond should be same, because this would indicate these 2 bond lengths should be different. However, if you invoke the concept of resonance and delocalize the structure like this, then you can understand why the bond lengths become simple. So, a structure where the 2 canonical representations are given, each one has a single bond double bond character, but neither of this structure explains the equal bond length of carbon oxygen bond. So, the structure should be somewhere something like this, for example, where the negative charge is essentially delocalized on both the oxygens equally, and this would be the hybrid structure, hybrid of structure 1 and structure 2 essentially. If you equally delocalize the negative charge on both the oxygen, then the probability that this carbon oxygen bond and this carbon oxygen bond will be equal in nature. So, this is an example of a resonance structure of this particular molecule. Similarly, there are several examples that one can give for the resonance structure. This is a alpha beta unsaturated ketone. Once again, because of the electronegativity difference between the carbons and oxygen, one can delocalize the charge onto the because the electron movement is towards the more electronegative oxygen, this carbon acquires a positive charge and the oxygen acquires a negative charge, for example. So, this would be a resonance structure of the alpha beta unsaturated molecule. So, the concept of resonance is extremely important. One other example that I can show is with respect to benzene. Benzene is a very classical example of a molecule which shows resonance structures. Most of the benzene and benzene derivatives do have the resonance effect in this particular manner. Let us take the example of benzene. The resonance structure proposed by Kekulé is an alternating double bond structure like this. So, benzene structure cannot be represented by either of these structures. Either of the structures suggests that there is an alternating double bond and single bond, but now we know from spectroscopy as well as from X-ray crystal structures, all the 6 carbon-carbon bonds are equal length. That is the reason the benzene structure is best represented by either a circle around the 6 carbon, indicating that this is a completely delocalized system. How do you delocalize it? By pushing the pi bonds around the ring system like this. Remember, we are touching only the pi bonds and not the sigma bonds in this structure. Or one can write the benzene structure as dotted line structure like this, indicating there is a complete delocalization of the electron around the 6 carbon. In other words, the electron density on each one of the carbon will be identical electron density and the bond lengths are identical. So, it is a highly symmetrical D6H structure. Symmetry is what we are having, highly symmetrical with a 6-fold axis of symmetry in this molecule. Now, what is a plus R effect and a minus R effect? As mentioned, the functional groups in a molecule can be classified either as the let us consider this particular molecule. This is methyl vinyl ether. If one were to write the resonance structure of this particular compound, one would simply take the lone pair of electron from the oxygen, push it onto the carbon here. Remember, the resonance effect here indicates that the lone pair on the oxygen can be donated. This is a negatively charged and this is a positively charged system. This is very different from the inductive effect you would have written for this compound. If you were to write the inductive effect, oxygen is more electronegative than carbon, so the inductive effect is going to be operating in this one. So, oxygen is a minus I effect because of the fact that it is more electronegative than carbon. But the lone pair on the oxygen can be delocalized onto the pi bond which is in conjugation. In other words, this phenomenon is known as conjugation. In other words, the orbital bearing the lone pair of electron on the oxygen and the pi orbitals can interact with each other, and thereby the electron density can be delocalized onto this carbon bearing a negative charge in this particular position. Oxygens bear the positive charge. This kind of an effect is known as the plus R effect, positively inductive effect. Suppose the same vinyl group is conjugated to a carbonyl functional group, for example. Now, you will have exactly the opposite effect. This is a easily delocalizable system and so is this easily delocalizable. So, the delocalized structure is going to have negative charge on the oxygen and a positive charge on the carbon. It is exactly reverse of what we did earlier. This will be a minus R effect. Please remember, in all these structures, between the two structures, neither of these structures do have a permanent existence to explain the reactivity of the molecule. It is the hybrid structure between these two structures is what is going to explain the reactivity of the organic compound that you have. For example, if the question is asked, if this molecule were to react with a proton, where will it react? It can react here, the lone pair can be protonated. It can react here also because it is partially the electron density according to this resonance structure is high. This is a completely octet obeyed resonance structure, so it is a valid resonance structure. So, the protonation can also take place here. In fact, vinyl ethers undergo protonation, the double bond, the terminal carbon of the vinyl group, for example. Resonance structures where the canonical structures are represented, they are represented by a double headed arrow. Unlike an equilibrium arrow, which is a two-side arrow, for example. Let us say, for example, this is the resonance structure. This is represented by a double headed arrow like this, and not by an arrow like this, which is reversible arrow. One cannot use a reversible arrow to represent the important point that one needs to remember for writing the resonance structure is 1. Lone pairs and pi electrons can be delocalized and not the sigma electrons in a molecule. Secondly, the resonance contributing structures are represented by an arrow which is a double headed arrow. Thirdly, no positional, no change in the relative positions of atoms. In other words, you cannot break sigma bonds in a resonance structure. That is what essentially means. If you break a sigma bond, the position of atoms will change quite drastically. So, there is no change in the position of the atoms. Fourth point is the canonical structures are non-existent. In other words, the individual structures are non-existent. It is the hybrid structure which represents the overall structure of the reactivity. The hybrid structure is representative. Of the true nature of the molecule. Oftentimes one cannot write the hybrid structure properly, like in the case of benzene, for example, you draw it with a circle or with a dotted line, as the case may be. Now, let us look into some more examples of the resonance effect of the plus R and minus R effects in aromatic system. Let us take the example of aniline. Now, aniline, the nitrogen has a lone pair of electron. So, one can write the pi electron density around benzene is, for example, in this particular fashion, donut shaped pi electron density on the top as well as in the bottom of the molecule. If the nitrogen lone pair also in the same plane as the plane of the benzene ring, for example, the plane of the pi electrons in the benzene ring, for example, then there is a possibility of interaction between the pi electron of the benzene and the lone pair of electron of the nitrogen. One of the principal requirement for delocalization of the electron is the orbitals have to be in the same plane. If the orbitals are in the same plane, it facilitates the lateral overlap and thereby delocalization can be written. So, one can write the delocalization of electron in this particular manner. We are not violating any octet structure here, please follow that rule also carefully. So, fifth point here is octet rule not violated. So, this is one of the resonance structures of aniline. One can also delocalize this structure in this particular manner. We can proceed further to delocalize this manner, for example. So, these are resonance canonical structures of aniline. What it tells us is essentially the electron densities in these positions, namely the ortho position and the para position of the aniline ring, have higher electron density compared to the meta position, because if we look at all these structures, the negative charge or the higher electron density is present in the ortho carbons and in the para carbon, but not in the meta carbon. You do not have a delocalized structure with the meta carbon having a negative charge. So, from the resonance structure we conclude that aniline has higher electron density in ortho and para positions. Ortho and para positions. This would mean that any electrophile or an electron deficient species will react with aniline in the ortho and para position. That would explain the reactivity of aniline to undergo substitution reaction in the ortho and para position, which we will see a little later. So, the effect that is shown in the case of aniline would correspond to a plus R effect, because it is a positive reinforcement of electron onto the ring corresponding to that particular structure. So, this is an example of plus R effect. Let us take an example of a minus R effect. For this you need to have a electron withdrawing functional group. Let me take the famous nitro functional group as the electron withdrawing functional group, this particular manner. The oxygen has the necessary number of lone pairs of electron, for example, to represent this structure. The nitro group itself can undergo the resonance structure in this particular manner. This is within the nitro group of the nitrobenzene. Without violating any octet rule, for example, we have drawn this particular structure. One can also, for example, because of the electron withdrawing nature of the nitro functional group, delocalize the pi electron from the aromatic ring onto the nitro functional group. This can also be done. So, that particular structure, if you follow the arrow which is indicated by the red chalk here, the delocalization of the pi electron from the ring essentially creates a positive charge on the ring and the negative charge on the oxygen, because oxygen is electron withdrawing or the nitro group is electron withdrawing group. Here the nitrogen is electron donating. One can proceed further with the delocalization. And move around the electron further down. Like this. So, these are all canonical structures of the or the resonance structures of the nitrobenzene. Nitrobenzene, if you want to describe fully the electronic effects, this is electron withdrawing by both the inductive effect. So, it is a minus I effect as well as minus R effect it has. That is why it is one of the powerful electron withdrawing functional groups in organic chemistry. On the other hand, if you want to describe the electronic nature of the aniline itself, it is inductively electron withdrawing because of the difference in the electronegativity effect. So, it is a minus I and plus R affecting group is what the amino functional group is. So, one can, based on this example, one can illustrate the point of resonance effect by means of aniline as an example for the plus R effect and nitrobenzene as an example for the minus R effect. The next electronic effect is known as the hyperconjugation effect. Hyperconjugative effect. Here again a CH bond that is attached to a unsaturated system, either a double bond or a triple bond, undergoes delocalization of electron. Let us say, for example, this is the pi orbital of the ethylene unit. Suppose if there is a carbon that is attached with the hydrogen that is present here. If the carbon hydrogen bond and the pi bond is coplanar, then one can draw the orbital of the sigma orbital of the CH can be drawn like this, 1s electron overlapping with the, here this is an sp3 hybridized carbon. A methyl group is what we are representing. In other words, structurally this would correspond to CH3, CH double bond CH2. A propene molecule is what we are referring to as the system here. If these three orbitals come to coplanarity, then there is a possibility of delocalization of electron of the sigma bond delocalized onto pi orbital. And this is a kind of effect which is known as the sigma resonance effect, and this is also known as the hyperconjugative effect. In other words, this is conjugation, this bond is in conjugation with the pi bond, and as a result of that, the structure that one normally writes is as if the electron density from the carbon hydrogen bond is completely donated onto the vinylic group, representing this particular structure like this. And this is what is known as there is no complete breaking of the carbon hydrogen bond, but traditionally it is the hyperconjugative effect is represented as if there is an ionization of the carbon hydrogen. In fact, there is no ionization of the carbon hydrogen bond. This is only a canonical structure that is represented by the charged separated structure like this. Please remember, one of the cardinal rule of delocalization is that you do not break the carbon bond or a carbon hydrogen bond, which is a sigma bond. So, this is not completely broken. There is a delocalization of the electron density from the sigma orbital of the CH bond onto the pi bond, and that is known as the hyperconjugative effect. Hyperconjugative effect essentially explains the stability of thermodynamic stability of, for example, this one compared to this one. A fully substituted double bond is more stable thermodynamically compared to an unsubstituted double bond like this. Here there are no groups which can lend hyperconjugation effect in the case of ethylene, whereas here there are 12 hydrogens which can participate in hyperconjugation effect. So, as you go from the tetra substituted to tri substituted to di substituted to mono substituted alkenes, the thermodynamic stability goes down in the series. This is thermodynamically most stable. One of the explanations that is given is that it has 12 hydrogens which can hyperconjugate and stabilize delocalize the sigma electron onto the pi orbital, thereby imparting stability towards the overall effect. Hyperconjugation effect is also responsible for explanation of the stability of carbonium ions. Suppose if it is a carbonium ion center, carbonium ion is having a empty p orbital by virtue of a positive charge associated with this one. So, the adjacent carbon hydrogen sigma bond can essentially participate in delocalization of electron from the hybridized sp3 hybridized CH sigma bond, that electron density essentially get delocalized onto the empty p orbital of the carbonium ion. So, if you consider the carbonium ions, methyl carbonium ion does not have an alpha CH, there is no carbon adjacent to it. So, this is the least stable of carbonium ions as compared to, for example, an ethyl carbonium ion, where there are three CH3, there are three CH bonds which can hyperconjugate with the. So, essentially what I have written here is CH3, CH2 plus is what I have written. So, three of these hydrogen at a time, one of the carbon hydrogen bond can be coplanar with the p orbital, empty p orbital. So, there are three hydrogens which can hyperconjugate here. If you go further to isopropyl cation, there are 6 hydrogen which can hyperconjugate here. Finally, tertiary butyl cation, which is this particular cation, there are 9 hydrogens which can hyperconjugate with this compound. So, the carbonium ion stability essentially because of the hyperconjugation increases in this particular direction. The tertiary carbonium ion is more stable than the secondary, which is more stable than the primary, essentially because of the hyperconjugation effect of the delocalization of a CH sigma bond onto the pi orbital of the carbonium ion, MTP orbital of the carbonium ion. Now, let us look at some types of reactions and then proceed further. Organic reactions can be classified in several categories. We will see some of the categories in this particular lecture, in the remaining portion of the lecture. Let us look at types of bond fission. Now, reactions takes place by breaking and making of bonds, sigma bonds, pi bonds and so on. So, the mode by which the bonds are broken is important to understand the reaction mechanism of chemical reactions. Suppose you take a molecule AB. There is a pair of electron which is the bonding electron between A and B if it is a sigma bond. Suppose if the bond breaks in such a manner that they equally share the electron density between the two atoms, then it is called homolytic band, homolytic fission. In the homolytic fission, one of the electron goes to B, the other electron goes to A. So, as a result of that, A and B now have an odd electron present in them. So, it will produce a radical, A radical and B radical. Such a process is known as the homolytic fission. A simple example can be seen by taking methyl iodide, for example. If you shine light on methyl iodide, in other words leave it open in the room light, it absorbs the energy of the photon and thereby producing a CH3 dot and I dot. Eventually the I dot will go to I2, so it produces the iodine color. The CH3 dot of course will go to ethylene, ethane and so on. So, this is an example of a homolytic. The pair of electrons that was originally present in the bonding orbital, one of them goes to iodine, the other one goes to the carbon. So, the carbon now is devoid of an octet, it is having only 7 electrons and that is why it is called a radical. This is methyl radical is what is represented by this structure. The methyl radical has a structure which is represented by having a orbital containing only one electron. One can also think of homonuclear diatomic molecules like chlorine and bromine upon photolysis, for example, or upon strong heating can undergo homolytic bond cleavage to give 2 chlorine radical or 2 bromine radicals, for example. So, these are all some examples of homolytic fission in terms of the bond breaking. If you have a peroxy bond, as in this case of dibenzoyl peroxide, this is a homolytic bond cleavage process is possible. It can produce a carboxyl radical, 2 carboxyl radicals can be produced, from which of course carbon dioxide can go. A phenyl radical can be produced. In other words, a phenyl radical is one where you have 5 hydrogens on the benzene ring, and one of the carbon has a radical which is the phenyl radical. That orbital is shown in the form of a dumbbell here, and this is a phenyl radical. On the other hand, one can also think about bond fission between A and B, where based on the electronegativity difference or the polarization of the bond between A and B, both the pair of electrons is taken by one of the partners, let us say by A itself or B itself in this particular case. So, A loses its bonding electron, so it gets a positive charge. B gains the additional electron, so it gains the negative. So, you produce a ionic species, and such a fission is called heterolytic fission. Heterolytic fission. Heterolytic fission produces charged species, whereas homolytic radical species is what is produced. Here radicals are formed, here ions are formed. Let us take the example of CH3Cl. Under suitable conditions, the carbon chlorine bond, which is already polarized towards the chlorine, can be broken, and one can produce a CH3 plus and a Cl minus. More easy to do reaction would be where one produces a tertiary carbonium ion. In other words, tertiary butyl chloride is even more reactive towards the heterolytic bond cleavage, because it can produce a tertiary butyl cation and a chloride ion. This kind of reactions are explained in the nucleophilic substitution reaction as to why tertiary butyl chloride undergoes what is known as a nucleophilic substitution reaction by a unimolecular process compared to a nucleophilic substitution reaction by a bimolecular process by methyl chloride, for example. So, the kind of bond fission essentially helps, understanding the bond fission helps us to understand the chemical reactivity of organic molecules. That is why it is important to understand the types of bond fissions that can take place. When you study organic reaction mechanism, what you are essentially studying is to understand the kind of bond breaking and bond making processes that take place in as much detail as possible. So, if you take an organic molecule, it reacts with some reagent, it forms some kind of intermediates, finally it forms some kind of a product. This is a general scheme that one can give to describe an organic reaction mechanism, trying to understand as much as possible the interaction between the reagent and the organic molecule, trying to understand as much as possible the structure and the nature of the intermediates that are produced, and finally of course the structure of the product one can elucidate by suitable spectroscopic methods and so on. Now, it is here we need to pay attention. These are intermediates which can be free radical in nature. So, one can have free radical reaction, one can have carbocation kind of a reaction, one can have carbon anion kind of a reaction as an intermediate. Finally, one can have carbenes as intermediates. Now, let us take the example of the free radical that we are talking about. Let us say, for example, I want to brominate ethane. Ethane is a saturated molecule, it is not a unsaturated molecule. In order to brominate it, you have to have free radical initiators or you have to have photon. H nu essentially means you are shining light on the bromine molecule. In that process it produces ethyl bromide and hydrogen bromide as the product. How does this reaction take place? This is generally explained by the fact that bromine undergoes dissociation in the presence of light to give two bromine radical. The bromine radical, once it is produced, it is a highly reactive intermediate. Remember, it does not have an octet, so it is a free radical. Free radicals are reactive intermediates, so it abstracts one of the hydrogens of ethylene, sorry, not ethylene, ethane, producing a ethyl radical plus HBr. Ethyl radical can now react with bromine, producing ethyl bromide and regenerate a Br radical. The Br radical now again go to another ethane molecule, do a hydrogen abstraction. So, this reaction is known as hydrogen abstraction reaction. Hydrogen abstraction reaction is what is. This is a homolytic dissociation. So, in the process you produce a alkyl radical. Alkyl radical stability depends upon the number of hyperconjugative group that is present in the radical system. Tertiary radicals are more stable than secondary radical, which are more stable than primary radical. Let us have a look at the carbocation kind of a reaction mechanism. As I mentioned earlier, if you put tertiary butyl alcohol in methanol as a solvent, methyl alcohol as a solvent, methyl alcohol is a polar solvent, it is a hydroxy compound. So, it is highly polar in nature. Under these conditions, the carbon chlorine bond undergoes ionization to produce a chloride ion. In other words, an already polarized carbon chlorine bond is now completely broken in such a manner that the pair of bonding electron is taken away by the chlorine, producing a chloride ion in generating a carbonium ion. Carbocation is what is formed. The structure of carbocation is that it is a sp2 hybridized system with an empty p orbital responsible for the positive charge. Let us say methyl carbocation would be, this would be 120 degree in terms of the bond angle. It is a planar system. So, it is like an sp2 hybridized carbon, for example, with an orbital which is an empty orbital containing no electron corresponding to the positive charge that you have in the system. So, we have seen what is a free radical and what is a carbocation. Carbanions are also reactive intermediates. Carbanions are generally generated by deprotonation reaction. Let us take this compound which is nitromethane. Because of the inductive effect as well as the electron withdrawing nature of the nitro functional group, there is inductive effect in all the carbon hydrogen bond also, which makes the carbon hydrogen bond an acidic bond. In other words, the acidity of this carbon is fairly high. So, if this is treated with sodium hydroxide, for example, sodium hydroxide can abstract a hydrogen, resulting in the formation of a carbanion and water. The counter ion here will be sodium ion, for example. The carbanion, of course, in this particular case, it is stabilized by delocalization onto the nitro-functional group. One can write resonance structures, for example, this carbanion, which would be this resonance structure. So, this is a formation of a carbanion as an intermediate in this particular reaction. Of course, this can further undergo condensation reaction and so on and so forth. One other example for carbanions preparation is the Aldol condensation reaction. If we consider acetaldehyde as a substrate, the alpha hydrogen of acetaldehyde, because of the inductive effect of the carbonyl functional group, again the carbon hydrogen bond is acidic in nature. If we treat it with sodium hydroxide, sodium hydroxide OH minus reacts with the hydrogen, producing a carbanion, which is this particular carbanion. Methyl carbanion is a highly reactive substance. It is known, methyl carbanion is known as methyl lithium salt, methyl magnesium bromide, for example. They are all examples of carbanion nature of the methyl group. The structure of the methyl carbanion is pyramidal in nature. It is not planar, because it has a pair of electron with an anionic charge. The structure is pyramidal in nature. In other words, including the lone pair of electron on the carbanion, it will be a tetrahedral structure. If you include this lobe along with these 3 hydrogens here, then it will look like a tetrahedral kind of a structure in this particular case. Finally, let us look at how carbenes are generated. Carbenes are typically generated by a reaction known as alpha elimination reaction. A carbene is a divalent carbon. Divalent sextet carbon. It has only 6 electrons around it. A simplest carbene that you can write is this particular carbene. So, if you look at the number of electrons around that particular carbene, there are only 6 electrons, 2 electrons of the 2 hydrogens and 2 electrons which is on the carbon, for example. Totally 6 electrons are there. It is an incomplete octet system. So, it is a highly reactive intermediate in organic chemistry. In principle, if we take chloroform and treat it with a strong alkali, not chloroform, I am sorry, methyl chloride, treat it with a strong alkali, something like 50% aqueous sodium hydroxide or potassium hydroxide. This reaction can in fact take place. Simultaneously, both the hydrogen and the chlorine are lost because of the presence of alkali. So, hydrogen chloride is eliminated, and in the process you end up with CH2, which is a carbene, which is the carbene that is produced, plus HCl. HCl, of course, is neutralized by the sodium hydroxide. On the other hand, dichlorocarbene can be produced by chloroform, reaction of chloroform. when chloroform is treated, because of the 3 halogen atoms are attached to the carbon, which have the strongest inductive effect in this particular system, when it treated with sodium hydroxide, it undergoes initially to produce a trichloromethyl anion. This will of course lose a chloride ion to produce CCl2, which is dichlorocarbene and a chloride ion. This is an example of an alpha elimination, because it is both the groups that are eliminated, namely hydrogen first, then the chlorine second, they are eliminated in a sequence, and this is known as the alpha elimination reaction. Resulting in the formation of the dichlorocarbene. So, what we have seen in this particular module is the electronic effects, particularly of resonance effect and hyperconjugative effect, and then we looked at the reactive intermediates, which are free radical, carbocation, carbanion and carbene type of intermediate. We will continue in the next model the kind of reactions that types of organic reactions that one can look at, and the kind of reaction mechanism that one deals with in organic industry. Thank you for your kind attention.